All right, kids, let's discuss isotopes. All right, so isotopes, this may be a term that you've heard of in the past. I'm not sure what context you know it in, or if you just recognize the name, but we're gonna figure out what these guys are today. Isotopes, all right? So you remember from studying atomic structure that the atomic number is unchanging and set in stone for atoms of each specific element. Meaning that, like, for example, carbon always has 6 protons. That number cannot change. If it does change somehow, then the element has lost its identity and it is no longer carbon. So what can change, though, is the number of neutrons that are in the nucleus of each carbon atom, or any atom, really. So the neutrons and the protons don't have to match up with each other, and there can be variations in the number of neutrons from atom to atom. And the variations in those atoms account for what we call the weighted atomic mass, which you'll find on the periodic table. So this is our periodic table that we use, and as you can see, the atomic masses for these guys, for the most part, are decimals. And that's pretty odd, because if we're just adding whole numbers of protons and neutrons to get a mass, it's pretty interesting that we would have decimal places. But these numbers actually represent a weighted average of atomic masses of individual isotopes. And we'll talk about that here in just a little bit. So let's, we'll define this term isotope here. Atoms with varying mass due to different number of neutrons are called isotopes. And here is a pretty good example of some isotopes of carbon. Okay, so carbon exists in 3 different forms. What's the same about all forms is this number here, the 6 protons, right? That number is set in stone. That's not going to change. But here we can see that we've got varying numbers of neutrons depending on the isotope that we're talking about. So by far the most abundant type is this type carbon-12. And carbon-12 has 6 protons and 6 neutrons. That's what accounts for the mass number of 12. And that's not a decimal, that's a whole number, all right? And then carbon-13, this is another less abundant type of carbon for sure, but this one has 7 neutrons. And so the 6 protons and the 7 neutrons give us a mass of 13. So the number that is after the name and after the dash, that symbolizes the individual atomic mass of a particular isotope. Carbon-14 is a much less common isotope of carbon, but you can see that with 8 neutrons here and our 6 protons, that's what gives us the mass of 14. Okay, so these are 3 different isotopes of carbon. Alrighty. So let's talk about this weighted atomic mass and how that's calculated. So there's some things you have to be told, especially about what we call the relative abundance. And so this example here is with chlorine's 2 isotopes. Chlorine exists in 2 different forms naturally as chlorine-35 and chlorine-37. That means that both of those chlorine atoms have 17 protons, but they do have differing numbers of neutrons, right? And it turns out that these numbers, you have to look these up, but chlorine-35 is a much more common isotope. It accounts for roughly 75.8% of the chlorine atoms out there, and the other 24.2% of chlorine atoms are this isotope chlorine-37. Okay, and so if we want to find, you'll notice here on the periodic table for chlorine, the weighted atomic mass is 35.45. So we're going to see how we're going to get that number. Okay, and so what a weighted average mass is just basically we give more weight to the isotope that has a higher relative abundance. And so it doesn't really make sense to just say that the average mass would be like 36 here, because so many more of the isotopes out there are closer to carbon 35 than 37. So it doesn't make sense to just split take a normal average of the masses. We want to give weight to the more abundant of the two isotopes, okay? And so here's the math that you're gonna do to do this. What you wanna do first is look at your relative abundances and turn them into a decimal by dividing by 100. And once you do that, you're gonna have decimals, and then you're gonna multiply the decimal by the appropriate mass. So the decimal form of 75.8, that's gonna end up being 0.758. You're gonna multiply that by 35, okay? And then the 0.242, you're gonna multiply that by 37. And then you're gonna add those two products together to find the weighted atomic mass, average mass, that is. All right, so here's what those terms look like. We have our 35, and I'll show this again here, 35 times the 0.758, and then we're gonna add that to 37 times the, this is I screwed myself up here, 0.242, don't put a decimal there, that's not right. And then when you multiply these two together, multiply, and then add the products, you get your weighted atomic mass. Okay, let's do an example with carbon. And I know I just showed 3 isotopes of carbon, but carbon-14 is so rare that I'm not even going to include it in here. The bulk of the abundance is made up by carbon-13 and 12 and 13. Okay, so we're just going to include those. And here are those percentages. Carbon-12 accounts for about close to 99% of the isotopes. Carbon-13 is just over 1%. So let's look at the average atomic mass. So here we're gonna say 12 times 0.989, and then we're gonna add that to 13 times 0.011. Okay, and I gotta get a calculator and I'll calculate that. So here's the math. Let's do 12 times 0.989 plus 13 times 0.011. And we're adding those terms together, and there's where our 12.011 comes from. Right, 12.011. And that's, I think, pretty darn close to what's on this table. 12.01, there it is for carbon. See it right there? So that's how that number is calculated. And then the other thing is, when you look at these decimals, if you rounded to the nearest whole number, that would be the most abundant of the isotopes. So 12.01 definitely rounds down to just 12, and that's a pretty good indicator that most of the carbon isotopes are carbon-12. Just like most of the boron isotopes are boron-11. Most of the aluminum isotopes would be 27. So just think about rounding those things up to the nearest whole number or down or whatever, and the number you land on is the most abundant of the isotopes. All right. So I hope that helps with isotopes. Oh, you know, one more thing I want to show you here is a couple of different ways to denote isotopes. We've seen stuff like this, like C-12. That's a real simple way of denoting a specific isotope. This would be carbon-12. You might see it with the name, carbon-12. Same thing here, just we're using the symbol instead of the name. And then the other way you can see this is with the symbol of the element, and then we put the the isotope mass, like 12 would go up here, and then the atomic number down here. So this is the isotope mass, and this is always the atomic number. All right, And so you'll see isotopes listed in all three ways from time to time. Okay, now I think I'm done. Hope that helps.